Hello, this lecture is about approximation algorithms. We are going to see a few examples of approximation algorithms and also draw connections to kernelization where appropriate. And we're going to see that often ideas used in approximation are used in kernelization and vice versa. The first thing to note is that approximation algorithms are not necessarily a good idea for every kind of problem. Take, for example, the satisfiability problem. For our particular application that we have in mind, it might not make sense to, for example, approximate the number of clauses we can satisfy, because maybe we really need all the clauses to be satisfied for the solution to make sense. Okay, so for an approximation algorithm, we need to have an instance that satisfies some properties. Like there should be something that we want to optimize. And so we're going to say that an optimization problem is characterized by a set of input instances, a set of feasible solutions, so possible solutions for each of the input instances, and also a value that tells us how good this feasible solution is. And in a maximization problem, the goal is to find a feasible solution with maximum value. For a minimization problem, we are going to try and find a feasible solution with minimum value. And so the value of the feasible solution here is what we want to approximate. For example, in the vertex cover minimization problem, the input is a graph G. The feasible solutions are all the vertex covers of this input graph G. And the value of a vertex cover is its size, so the number of vertices we selected into our vertex cover. Okay, so since vertex cover is a minimization problem, now in an approximation algorithm, we might want to find a small vertex cover, but it's not necessarily the smallest one. But still we want to have a guarantee on how close it is to the smallest vertex cover. And this brings us to the definition of approximation algorithms and approximation ratios. So an approximation algorithm for an optimization problem is a polynomial time algorithm that returns a feasible solution. Now, if we denote by a of I, the value of the feasible solution that is returned by the approximation algorithm for an instance I, and by opt of I, the value of the optimum solution for this particular instance I. So if pi is a minimization problem, then the approximation ratio of the algorithm A is R if the value of the solution returned by the algorithm divided by the value of the optimum solution is at most R for every instance I. So no matter what instance we give to the algorithm, it will return a feasible solution whose value is at most R times the optimum. So that's for minimization problems. For maximization problems, the approximation ratio of the algorithm is R if opt of I divided by A of I is at most R for every instance I. And so this difference in definitions for minimization and maximization problems is just so that approximation ratios are always at least 1. Okay, so we say that A is an R approximation algorithm if it has approximation ratio R. And so notice that if your algorithm is a 2 approximation algorithm, then it is also a 3 approximation algorithm, because if the approximation if this ratio is at most 2, then it's also at most 3, right? Okay, let's go to our first example, which is multi-way cut. And what's this problem? So The input is now a connected graph G, so like the graph on the bottom here. And we also have as input a set of terminals. So and the terminals are the wet vertices here. Those are our terminals. And we have k terminals in the input. Now, what's a feasible solution? So in a feasible solution, we basically want to delete edges from this graph so that each terminal cannot reach any other terminal. So there's no connection anymore between any two terminals in the graph. So and the multi-way cut will be a subset of edges, such that if we delete this subset of edges, and here it's the red dotted edges, so if we delete those edges, then there's no path between any two distinct terminals anymore. So in other words, each terminal must have its own private connected component and cannot share a connected component with any other terminal. And so what we want to optimize here is we want to minimize the size of the multi-way cut. So the number of edges in this multi-way cut needs to be minimized. Okay. So one thing that we can notice here is that so we said already that every terminal must live in its own connected component. So if we take a terminal like A here, we have to cut it from all the other terminals. And our approximation algorithm that we are going to see will rely on this fact. Okay, so the problem is NP-complete, and even when we have just 3 terminals, and for k equals 2, so if we have 2 terminals, you probably know this as the min-cut problem. And so there's a nice duality between min-cut and max flow that enables us to solve the problem in polynomial time when k equals 2, so when we have just 2 terminals. Okay, so this is our approximation algorithm. It is a greedy algorithm. So it goes through each of the terminals. So we have k terminals, S1 to Sk. Now for each one of them, we compute a smallest set of edges that separates this particular terminal from the other terminals. So to make sure that this terminal Si lives in its own connected component and cannot reach anybody else. And so by the previous algorithm, this can actually be done in polynomial time, because what could we do? So if we want to cut A, for example, from all the other terminals, what we could do is we just merge all the other terminals into one terminal, and then find a minimum cut between these two terminals that result from this. So between A and this merged node that represents all the other terminals. Okay, and then, so we do this for every terminal. We compute the smallest edge set that cuts this terminal from the others. And then we return the union of all the edge sets that have been computed in this way. Okay, so this is a polynomial time procedure. I think it's quite obvious that it produces a feasible solution. So in the end, if we take the union of all those sets Ci, then we indeed get the multi-way cut. Okay, but what can we say about the approximation ratio? So we fulfilled these conditions here that so this is a polynomial time algorithm. It returns a feasible solution. But now we want to say something about the approximation ratio. And here we have a minimization problem. We want to minimize the size of the multi-way cut. So we need to establish some relationship between the size of the cut that is returned by the algorithm and the size of the smallest possible cut that an instance could have. Okay, so if we look back at this example now, our algorithm would not actually compute this cut because, for example, for separating A from all the other terminals, there is a smaller cut, so it would select this edge AB. To separate D from all the other terminals, it might compute, well, the edge DB and also DF, let's say. Now to separate E from all the other terminals, it might compute the edge BC and, for example, FG. Okay, now if we take the union of all of these edges, we get the feasible solution, but its size is not minimized because we produce a solution of size 5, whereas there exists a solution of size 3. So what we can observe here that, well, to cut D from the other terminals, well, instead of using the edge DF, we could have used the edge FG, right? And now basically we benefit because we can share this edge between two solutions for two individual terminals. Right, so now we get a feasible solution of size 4, and now also for the edge A, for the vertex A, to separate it from all the other terminals, well, we shouldn't have used the edge AB to cut it, but the edges DB and BC. So could have used those twice as well. Okay, so if in the end we look at our optimal cut and we observe that each of the edges that occur in this cut, it will connect exactly two different connected components that result from deleting the edges of the multi-way cut. And so when we look at these two components, ideally we would have shared as many edges as possible when cutting these two components from the other terminals. So what could go wrong in this greedy algorithm is that it doesn't really take into account that some of these partial cuts can be shared between the various components. Okay, but since each of those edges in the cut connects at most two connected components, we will actually be able to prove that greedy MC is a true approximation algorithm for multi-way cut. So let's see how this works. Okay, so we already noticed that the algorithm runs in polynomial time. Now, we also observed that it produces a feasible solution. To show that its approximation ratio is at most 2, we will now compare the size of the solution it returns, which is the union of those CIs, to the size of an optimal solution. Let's call the optimal solution A. Now, the graph, when we remove all the edges that are in A, so this resulting graph has k connected components, because we started from a connected graph and we didn't remove any superfluous edges, so we didn't add any dummy edges to our solution. So we will get exactly k connected components, namely 1 for each of the terminals. Now, AI is now the set of edges that have one endpoint in GI. So GI is one of the connected components. AI is those edges that go out of this connected component and separate this connected component from all the other terminals. And now, of course, so the optimum solution is the union of the AIs. Now, since each edge of A is incident to two connected components, we have that, well, if we sum the size of the AIs, we get exactly 2 times the size of A. Okay, so 2 times the size of A equals the sum of the sizes of the AIs. Okay, so what was an AI? It was those edges in the optimum solution that separated the connected component I from all the other terminals. But CI was the smallest such cut that cut this particular terminal from all the other terminals. So we know that each AI has size at least the size of CI. So CI is the one that's returned by our algorithm. And so since the algorithm computed here a smallest subset CI, we know that AI, the cardinality of AI is at least the cardinality of CI. Okay, and so when taking the union of all the CIs, we get a set whose size is at most the sum of the sizes of the CIs. Because some of the edges could be shared or not, we don't know. So, but we know that taking the union of those gives us a set, and the size of the set is at most the sum of the sizes of the CIs. Okay, so if we look here, what we have is that we have that 2 times the size of A is at least the size of C. So the solution that we get, so the size of C, is at most 2 times the size of the optimum solution, and therefore greedy MC is now a true approximation algorithm. Okay, let's move on to vertex cover. So what have we seen for vertex cover already? Well, we saw the definition. So the input is graph G and an integer k, the parameter is k, and the question is whether G has a vertex cover, so a set of vertices that cover all the edges of the graph of size at most k. We also saw a preprocessing algorithm that took as input an instance for vertex cover and produced an equivalent instance for vertex cover. So we only know that the output is a yes instance if and only if the input is a yes instance. So now if we want to use this preprocessing algorithm for an approximation, then, well, in the approximation algorithm, we actually need to produce a feasible solution. So we need to add some bookkeeping to this preprocessing algorithm. And just remember which vertices did we actually mean to put into our vertex cover when executing these simplification rules. So for the degree 0 rule, we actually didn't want to put any vertex into our vertex cover. For the degree 1 rule, we meant to add the neighbor of the degree 1 vertex into our vertex cover. In the large degree rule, we meant to add this vertex with degree more than k in our vertex cover. And for the number of edges rule, we just returned no. So I claim that it's easy to add some bookkeeping to this preprocessing algorithm so that it outputs also a set of k minus k prime vertices such that any vertex cover of the resulting instance can be extended to a vertex cover for G by adding these k minus k prime vertices. Okay, so let's try and use this preprocessing algorithm to get an approximation algorithm for vertex cover. So one thing that we notice is that so the output of our preprocessing algorithm has size bounded by order k squared. And so for any graph, there's always a trivial vertex cover, which is to put all the vertices of the graph into the vertex cover. So if we did that here, actually we would get a set of order k squared vertices that cover the remaining edges that need to be covered. Our bookkeeping now also adds these k minus k prime vertices, but in total we still have order k squared vertices, right? So if we knew k before starting, then we could easily do this. So now we just need to have a procedure that tries out many values for k until it succeeds. So this corollary here will tell us that so the vertex cover optimization problem has an approximation algorithm with approximation ratio order opt. So we start from k equals 0 and we increment k until a solution is returned. So for a given value of k, we first of all kernelize. So we use the pre-processing algorithm to compute a kernel. So in case the number of edges rule did not return no, then we can return a vertex cover containing all the vertices of the kernelized graph along with the vertices determined by the bookkeeping of the kernelization procedure. So if this procedure succeeds, then it returns a vertex cover of size order opt squared. And now we just need to compute the ratio of the returned vertex cover, which has size order opt, and the optimal vertex cover, which has size opt. So and the ratio is of course order opt. And this is our approximation ratio for the vertex cover optimization problem. And now there's an obvious question. If we have an approximation ratio of order opt, can we get a constant approximation ratio? And so now we will see another kernel / approximation algorithm for vertex cover. Okay, so the vertex cover problem can be written as an integer linear program. So what is this? So we can have a reduction from the vertex cover problem to an integer linear program. So what is an integer linear program? Well, it's something like this here. So we need to minimize some objective function, and so this function should be linear, subject to some constraints, and all of these constraints should also be linear. And now we have some variables, and these variables, they can either be integer variables or just real variables. So for linear programming, we are not allowed to have integer variables. For integer linear programming, we are allowed to have integer variables. So we are able to restrict some of the variables to be integers in some domain, and here we restrict xi to be either 0 or 1. Okay, so what do we have here? So now for an instance for a vertex cover, so that's composed of a graph G and an integer k. So let's name the variables v1 to vn, and so I meant we name the vertices v1 to vn, and now we create the variable xi for each vertex vi. And now our set of variables for the integer linear program is this set x. That's composed of x1 to xn. Okay, so for each graph G, we now have an integer linear program that expresses vertex cover. So what do we do here? So the meaning here behind this is that we have these variables xi, and we will set a variable xi to 1 if we add the corresponding vertex vi into the vertex cover. And we set xi to 0 if we don't add the corresponding vertex to the vertex cover. So so when is a set of vertex cover? So each edge of the graph needs to be covered. And we can express this here in our integer linear program by saying that for each edge in the graph, we need that, well, either the variable corresponding to the first vertex is equal to 1, or the variable corresponding to the second vertex is equal to 1, or both of them are equal to 1. So we have that xi plus xj must be at least 1 for each edge vi, vj in the graph. And since we want to compute the small vertex cover, we want to minimize the sum of the xi's. So we want to minimize the number of xi's that are set to 1. And so this is now our integer linear program. So solving this one is equivalent to solving vertex cover for the graph G. Okay, so G comma k is a yes instance if and only if the objective value for this integer linear program is at most k. So the objective value is the value of this objective function here, which is the sum of the xi's. And so since we just reduced the NP complete vertex cover problem to ILP, to integer linear programming, we conclude also that ILP is NP hard. Okay. So this is a program that's very similar, but it's a linear program. And the only difference is that we relax the constraint that the xi's must be 0 or 1. So now we say that the xi's must be at least 0, so they're real variables, they can take fractional values. And we just say that they must be at least 0. So that's the only difference here. And now we get a linear program. So we got rid of the integer constraints. So this is now a linear program. So we can observe that, well, since we didn't add any constraints, but just removed constraints, we made it easier to minimize this function. So now the value of an optimal solution for the linear program is at most the value of an optimal solution for the corresponding integer linear program. It turns out that linear programs can be solved in polynomial time. So the fastest known algorithm is by Cohen, Lee, and Song from 2019. Okay, so now basically this is a polynomial time solvable solvable problem. And this expresses exactly what we want to solve. So now if we want to use the linear program as an approximation for the integer linear program, we need to establish some kind of relationship between the two. Okay. So let's think about properties of the LP optimal solution. So for the linear program, how does our solution look like? So I'll partition the variables into 3 sets. So first of all, we have those variables whose value is less than 1/2. Then we have those variables whose value is equal to 1/2, and then we have those variables whose value is more than 1/2. Okay, so let me draw this here. So here we have what's it called? V minus. We have V plus, and then V 1/2. Okay, so what can we observe now? We can observe that, so these were all the variables that had value less than 1/2. So in particular, we can notice that, well, there's no edge here. So if we have two variables inside V minus, then the corresponding vertices do not have an edge between them, because otherwise we would violate the constraint that xi plus xj must be at least 1. So we notice that V minus is an independent set. The other thing that we can notice is we have the same property if we have a vertex in V minus and a vertex in V 1/2. Also, we cannot have an edge between these two vertices, because so we have value 1/2 and something that's less than half. So in total, it's the sum is less than 1. So we cannot have such edges. So, which means that all the neighbors of V minus must be in V plus. So V plus is the neighborhood of V minus. Okay. So that's two simple properties we can already observe. We can also observe that it doesn't make sense to have to assign values to variables that are more than 1. Why is that? Well, because all the values are at least 0. So if we assign a value that's more than 1 to any variable, we are basically wasting. We are artificially increasing the objective function, and we don't need to, because, well, no constraint will ever require us to have values that are more than 1. So we said that V minus is an independent set, and also the neighborhood of V minus is V plus. So here I got that V plus is neighborhood of V minus. We also have that for each subset of V plus, its neighborhood in V minus must be larger than the subset. So let's see. So we have some subset of V plus, and this holds actually for each subset of V plus S. If we look at the neighborhood in V minus, then that neighborhood must be larger than S. So why is this the case? So suppose actually we would have more vertices in S than in its neighborhood in V minus. I claim that then we could get a better solution. So we could get a better solution because, so what are the constraints that we have? So if we look at the vertex in S here, it might have some edges to V 1/2, it might have some edges to other vertices in V plus, but for all of those, we have some slack. So because all of these edges are covered by values that are more than 1. So if we take the sum of the values of the endpoints, we get something that's more than 1. So potentially we could decrease the value that we assign to this variable. Except there's some problem, namely, well, this variable, it might have some neighbors in V minus, right? So that's the only thing that could hinder us from decreasing these values. But now, if actually S is larger than its neighborhood in V minus, we could decrease each of the values of S by some, so all of those, for all of those, we decrease their value by some small value epsilon, and for all of those in V minus that are neighbors of S, we add the same value epsilon to all of them. So in total now, if S is larger or at least as large as V minus, then we still get a feasible solution. Because, well, for all of these edges here between S and its neighborhood in V minus, we didn't change anything. Because, well, these edges are still covered by the same sum of values because we just subtracted minus epsilon from some of them and added epsilon to the others. Okay, so, and our proof now says that, well, for the sake of contradiction, suppose there's a set S in V plus, such that the size of S is more than the size of its neighborhood in V minus. So, and this value epsilon here that I select is the minimum of the values of the xi's that are in the set minus 1/2. So basically the slack that we have beyond 1/2. And now I define a new assignment of values to all of the variables. And basically for those that are not in S or its neighborhood in V minus, I don't touch them, so I leave them the same. So that's all of those. Now for all of the vertices in S, we decrease their value by epsilon, and for all of the vertices in the neighborhood of S intersect with V minus, we add this value epsilon to them. And now we can observe that A prime is an improved solution for the LP. And this actually contradicts the fact that the solution we had in the beginning is an optimal solution. So how can we use this lemma, lemma H? Well, we can use it by looking at Hall's marriage theorem. So Hall's marriage theorem says that in a bipartite graph, so in a graph where we can partition the vertex set into two independent sets, so all the edges are in between the two sets, but we don't have any edges inside any of the sets. There is a matching that saturates S. So here we have V and U, and let's say S is a vertex set, and now there's a matching that saturates S. So a matching is a set of edges in the graph that don't share any endpoints, and it saturates S if each vertex from S is incident to an edge of the matching. So we have such a matching if and only if for every subset of S we have that the subset is smaller or equal than the size of its neighborhood. Okay, so there's two ways to this theorem. One is, so if we have such a matching, then we have that for every subset, the subset is smaller or equal than the size of its neighborhood. And also if the size of the neighborhood is smaller than the set itself, for every set that's a subset of S, we have that there's then a matching that saturates S. So, okay, so in our case here, what do we have? So we said that this property holds for every set S in V plus. So by using Hall's marriage theorem, let me clean up this a bit. So now we conclude that we actually have a matching that saturates V prime. So that's a special case where the set is the whole of the one side of the bipartition. So we can say that now we must have such a matching where every vertex of V prime is saturated. In V minus, we might have additional vertices that are not saturated by the matching, but everybody in V plus is saturated. Okay. And we obtain this by considering this bipartite graph that goes in between V minus and V plus. So ignoring all the edges inside V plus, there's no edges inside V minus anyway, but looking at all the edges that go across, we can observe that such a matching must exist. So in this graph we have matching of size, the cardinality of V plus. So the size of matching is the number of edges. So the number of edges of the matching is equal to the number of vertices in V plus, meaning that every vertex in V plus must be saturated. And the proof is just by using the previous lemma that we had and Hall's marriage theorem. Okay. So next I want to define Quown decompositions. And what's a Quown decomposition of a graph? It's basically exactly this. So it's a partition of our vertex set of the graph into 3 parts. So on top here we have the Quown, then we have the head, and then we have the body. The constraints are that, so the Quown is an independent set, and it is non-empty, so it contains at least one vertex. So let's see, so the Quown is C, the head is H, and the body is B. We have that the head is the neighborhood of the Quown. We have that the body is all the remaining vertices, so that's the vertex set minus C and H. And we have that this matching must exist, so the matching that goes in between the Quown and the head, and that saturates every vertex of the head. So let me just check whether this is exactly what's stated here. So we have that the Quown decomposition CHB of graph G is a partition of the vertex set into sets C, H, and B, such that the Quown C is a non-empty independent set. The head is the neighborhood of the Quown, the body is all the remaining vertices, and there's a matching inside this graph between the head and the Quown that saturates the head. So if it saturates the head, it must have size, cardinality of the head, and so the only difference is here that the theorem, if we have the head here and the Quown here, well, since the Quown is an independent set, so the definition here doesn't directly restrict that the matching cannot contain edges inside the head, but this is implicit because, well, the Quown is an independent set. So if there was an edge of the matching inside H, inside the head, then we would actually not meet the size restriction here. So indeed we have that, so the matching must go across from the head to the Quown, and every vertex of the head must be matched to somebody in the Quown. Okay, so this picture corresponds exactly to what we had. So by the previous lemmas, we obtain now a Quown decomposition where V minus is the Quown, V plus is the head, and V 1/2 is the body. In case that V minus is non-empty. Okay, so what have we done so far? So if we are given an instance for vertex cover, we can translate it into an integer linear program that's equivalent. Now we can relax it to a linear program that that can be solved in polynomial time. So if we solve the linear program and v minus turns out to be non-empty, so some variable gets value less than 1/2, then we can obtain such a Quown decomposition. And so this procedure is all polynomial. So in polynomial time, we either get a Quown decomposition, or we have that all the variables have value at least 1/2. Before continuing, let's reason a bit more about Quown decompositions. So I have given you two graphs here, and so we want to compute a Quown decomposition for each of them. So the Quown is an independent set, its neighborhood is the head, and we must have this matching between the head and the Quown. So let's see, so for the first graph, so let's put E into the Quown and C and G. So kind of we want to have a big Quown so that it's easy to match vertices from the head into the Quown. And we want that the Quown has a small neighborhood because we want this matching to exist, right? So now in the head, I have the neighborhood of the Quown, so F is in my head, D is in my head, and B is in my head, and A is in the body. And now, well, this matching exists because I can match every vertex from the head to a vertex of the Quown. Okay, so that's now a Quown decomposition for the first graph. What about the second graph? How could a Quown decomposition look like? Well, I have an issue here because, well, my Quown must be an independent set. This graph doesn't seem to have an independent set of size 3. It has independent sets of size 2 and of size 1 and of size 0. 0 is not enough because our Quown must be non-empty. So it should have size 1 or 2. But if I take any one vertex into my Quown, the neighborhood has size at least 3, and it will be impossible to match vertices from the neighborhood into the Quown. And actually, even taking 2 vertices into the Quown, I still have the same problem because the neighborhood is just too large. The neighborhood will have size 3, and so this matching doesn't exist. So this means actually that this graph doesn't have a Quown decomposition. Okay. So on the slides here I gave a different Quown decomposition for the first graph, and we observed that the second graph has no Quown decomposition. Okay, so I claim now that if our polynomial time algorithm has actually computed a Quown decomposition, then we can apply a simplification rule. And so I'm saying that here that the size of the smallest vertex cover, let's call this VC of the graph, so the size of the smallest vertex cover of this graph is at most k, if and only if the size of the smallest vertex cover of the graph induced on the body, so the graph obtained by just keeping the vertices of the body and deleting all the other vertices. So this graph has vertex cover number at most k minus the size of the head. Okay, let's see why this is the case. So here we have this partitioning of the vertex set, and we also have this matching. Now, okay, so in general, if we have some matching of a graph, so they cannot share endpoints, right? This is not allowed. So we have some matching plus some other vertices, that connect to the matching in some way. We don't really care about the other edges. So our vertex cover must cover all the edges of the matching. And all the other edges as well, but in particular the edges of the matching. So how can we cover the edges of the matching? Well, we need at least one endpoint of each edge of the matching. It could be the case that we need two of them to cover other edges, but we need at least one endpoint for each edge of the matching. So if we look back to our Quown decomposition here, we have that, well, in this case, our matching has size 3, so we need to have at least 3 vertices into our vertex cover if we want to cover the edges of the matching. But choosing all of the vertex cover inside V+, what does it do? So this covers all the edges of the matching and actually all the edges that go from V+ to V-. So even other edges from V+ to V-. It also covers all the edges that go from V+ to V1/2. There's no edges inside V-. So actually we cover all the edges that are not inside the body. So there's no edges inside V-. We observe that there's no edges from V- to V1/2. So everything is covered by taking V+ into our vertex cover. And we know that, well, just to cover the edges of the matching, we'll need cardinality of V+ many vertices. So basically we want to prove that this is optimal. So this is now our proof. If we have a vertex cover S of G of size at k, then S contains at least one vertex for each edge of the matching. So we have that if we take this vertex cover and intersect it with the crown and the head, so C union H. So we look at all the vertex cover vertices that are in the crown or the head, we get at least cardinality of H many vertices. And therefore now S intersect B, so the vertices in the body that are also in the vertex cover, so those form a vertex cover of the graph G induced on the vertices of the body of size at most k minus the cardinality of H. So the first part of the proof is just because we need at least cardinality of H many vertices to deal with the edges of the matching. And those will not help us cover anything in the body. And so now the second part of the proof is that, so if we have a vertex cover of the graph induced on the body of size at most k minus H, then just adding H to this vertex cover gives us a vertex cover for G. Because we observed that the head covers all the edges that are not in B, so it covers all the remaining edges. So what we have proven is the Namhauser-Trotter theorem, which says that there exists the smallest vertex cover that contains all the vertices from V+ and no vertex from V-. So after having computed the solution to the linear program, we can now add all the vertices that have value more than half to the vertex cover, delete all the vertices that have value less than half from the graph, and so what we are left with is just an instance where all the remaining vertices have value exactly 1/2. Now, if we actually add all these vertices of value exactly 1/2 to our vertex cover, we will get a true approximation. So dealing with the vertices with value less than half and more than half those were optimal choices. Now, for those vertices that have value exactly 1/2, what happens if you add them all to the solution? So we have to relate now what we are doing, so what our algorithm does, putting all of these vertices into the solution, to the optimal solution, or to one optimal solution. Okay, but what we know is that the linear program is a relaxation of what needs to be done for an optimal solution. So we know that basically, let's look at all the vertices that are left. So the linear program gives value 1/2 to each of those vertices. So we know that for an optimal solution, at least half of the vertices in total need to be added to the solution. This is because the value of the integer linear program is at least as large as the value of the linear program. So since at least half of the vertices need to be added to the solution, to an optimal solution, we know that adding all of them will give us a true approximation. So we can also formulate this as simplification rules. So we have the Crown reduction rule that says if solving the linear program gives an optimal solution where V minus is non-empty, so where at least one vertex gets value less than 1/2, then we can return the graph where we deleted the head and the crown, so we deleted V minus and V plus, and we decreased k by the size of the head, so we decreased k by the size of V plus. And then we have this number of vertices rule. It says, well, if solving the LP gives an optimal solution where all the vertices have value at least 1/2, and the number of vertices is still more than 2k, then we can return no. So the reasoning is the same as for the two approximation algorithm. Because, well, how do we prove that they are sound? So the Crown reduction soundness follows from previous lemmas. And now let's go a bit more into details for number of vertices. So consider an optimal solution alpha for the linear program. And suppose that it sets no variable to a value that's less than 1/2. So we know that the value of this solution is at least the number of vertices divided by 2. And therefore the value for an optimal solution of the integer linear program is also at least the number of vertices divided by 2. So, but the solution for the integer linear program is exactly the same as the size of a smallest vertex cover. So now, since G has no vertex cover of size less than 1/2 of the number of vertices, we have no instance if k is less than the number of vertices divided by 2. So the number of vertices rule basically gave us a solution whenever the number of vertices was more than 2k. So we can conclude now that vertex cover has a kernel with 2k vertices and order k² edges. So we still have order k² edges because we know that the number of edges is at most quadratic in the number of vertices. So we haven't really decreased the size of the kernel by a significant margin, but we managed to decrease the number of vertices. And this is the smallest known kernel for vertex cover. There's a link here that gives the current smallest kernels for various problems. Okay, so why does it help that we have decreased the number of vertices? Well, oftentimes when we now design a branching algorithm or some other exact algorithm for this problem, then it's often exponential in the number of vertices and not so much in the number of edges. So that's why it can help to also decrease the number of vertices.